It's our immense pleasure here today, this morning, to kick off the workshop, which we have rather ambitiously called ICD Days. It's also Valentine's Day, incidentally, right? So it's a great day to meet with quantum physics, the pioneers and experts in certain aspects of this wonderful science, which we all inherently love so much. That's why we are here, or those online would be online, and those who probably view this video later would also be doing it for the same reason. So it's a great day to learn as much as we can, almost from ab initio, as the first talk is going to say, about processes like ICD. But then every good workshop should have a session chair, and our program and agenda are very simple. So despite that, it's with a lot of pleasure, and it's my privilege to invite Professor Lawrence Sederbaum to chair the first session, and I hand it over to Lenz to take over.
Thank you, Shiva. Opening remarks. I think you already made opening remarks. So it's a surprise, but I'm a surprise, so to say, chairman. Okay, take. So, Nico, you have a title?
Computing resonance with.
Computing resonance. So, welcome and good morning. I'm still jet lagged, so if I fall asleep, please shake me a bit. No problem. Yeah? Okay. Go ahead. Thank you.
Okay. Thanks. So thanks, and thanks Shiva and Arvind for organizing this workshop. So I'm a chemist. I'm trained, which is more like in the atomic and molecular physics community. So I'm really something in between, and I use quantum chemistry to model this decay processes. So so we're going to decay processes in the next days, and one important characteristic of decay processes are the life from the time domain to is the decay width, and this is what I want to show you today, how in our group we compute this decay width. There are several ways to do it. I'm going to focus on the way we do it, which rely on the Fano feedback theory of resonances. Okay, since I think the audience is very diverse, I'm going to start with really basic quantum chemistry, because we need those ingredients to compute the resonance width. I'm not going to go really into detail in each part of this quantum chemistry. I'm not going to be even rigorous in the way I present it. It's just to give you a feeling of what is quantum chemistry and how we use it for computing the resonance width. Then I'll move to this final flashback theory, and I'll do the same. I won't be really going too much in detail. I won't be rigorous. Again, I just want to give you a feeling, some ideas of how we do it. So maybe later, if you see one of our papers or you encounter this kind of method, you'll be a bit familiar. Okay. So I apologize if when you read the paper, you see that I made some mistake in the equation I show. Really, the point is not to be rigorous here. The second thing I wanted to say before starting is that I prepared some notes, but it's not going to take 2 hours. So please stop me anytime you have questions. We can discuss and so on. Otherwise, I'll be finished early and we can move on. But I think the point for today's meeting is really to discuss. So really, anytime I'm not clear or you have questions, just stop me. Okay? All right. Let's get started. I'll start writing. Sure. Thanks, Eva. Okay, so let's start it. So I'll start with, I will assume that you all have some knowledge in, you know quantum mechanics, but no quantum chemistry. Okay, so I will introduce what we need for the quantum chemistry. So I'll start with the molecular Hamiltonian. So for a molecule, you can write the total. So it's really including nuclear motion and electron motion. So you have the kinetic energy of the nuclei, which I wrote Tn, the kinetic energy of the electrons, Te, the attraction between the nuclei and the electron. You have the repulsion between the electron and the, sorry. So I need sometimes to get used to this pen. And the repulsion between the nuclei. Okay, so it's very general. Okay, so as I said, kinetic energy of the nuclei, kinetic energy of the electron, the repulsion, the attraction between nuclei and electron, the electron-electron repulsion, and the nuclei-nuclear repulsion. That's the full Hamiltonian for a molecule. In the non-relativistic case, right? We're not going to talk about relativistic effect during this session. Okay. Solving the Schrödinger equation for this full Hamiltonian is far too complicated. So we have to introduce approximation. The first one that we use is the standard Born-Oppenheimer approximation. So I'll write it just BO. So that's for Born-Oppenheimer approximation. And the idea here is to separate the motion of the nuclei and the electrons. So we treat them separately. To do that, mathematically, it's just writing the total wave function, so for the electron nuclei, as a product of a term that depends only on the electron coordinates, right? And a wave function that depends only on the nuclei. Okay? Then you do the math, you do the adiabatic approximation to say that the electronic part doesn't depend on the nuclei, and you end up with two Schrödinger equations, one for the nuclei and one for the electron. So I'm going to write the one for the electron, so you get just HE VE equal EE VE. Okay, and HE is just this thing here. Okay, so that's the electronic Hamiltonian. Okay. Well, you can include it, the V and N, you can include it, it's just a constant in the Born-Oppenheimer approximation. So usually, because this energy, this EE, that's what we call the potential energy surfaces, usually we include this repulsion, and this is what you see, for example, for diatomics, that's why it raises, so we do include it. Yeah, but it's just a constant, you're right. So we could exclude it if needed. Okay. So that's the starting point. Once you have solved this problem, you can also treat the nuclei, and Krishna will talk about it tomorrow. So I'll leave this aside. Okay, and it's not that important for computing resonance width, decay width. Okay. So I should really mention that now we solve this electronic Schrödinger equation for fixed nuclei. Okay, so this Schrödinger equation is slightly easier to solve than the full Schrödinger equation. It's still not easy, and we still have to do some approximation most of the time. Okay, I will go into that. So I just to be sure, or maybe to detail a bit more, I'll write the electronic Hamiltonian for H2. just to, so far it was very general, but for H2, so you get the kinetic energy of the first electron, the kinetic energy of the second electron. You get the attraction between one atom of H2 and the first electron. Nope. The attraction between the second atom and the first electron, and then you get the same for the second electron. Then you have the electron-electron repulsion. Oops. And the nuclear-nuclear repulsion. Okay? And the real issue for us is this term here. That's the electron-electron repulsion. Without that, we could solve it exactly. Okay? So it's really the bottleneck or the problem here. I'm waiting a bit because I'm going to change page and then it will disappear. So, yep.
So in the Born-Oppenheimer, we write this as a product state of the electronic eigenfunctions and the nuclear
Yes.
eigenfunctions, right? But okay, in reality, this is an approximation. So in some sense, if, like, what are we losing out in making this approximation? What kind of information
Is lost when you that. Most of the time, really little. I mean, it's basically the coupling between the electron and the nuclei. So what you when you do the Born-Oppenheimer approximation, what you say is that I mean, with your, physically it means that the electron, they move much faster than the nuclei. Okay, so they assume that the electrons are fixed, right? Uh, the other way around for the nuclei, it's like they see just the potential created by the electron. Okay, so what you lose is that it's the response of the nuclei when the electron moves, and the other way around, the response of the electron when the nuclei moves. So this you lose it. That's basically one. You see what what I mean?
But my question is also, like, we are making the assumption that the states are separable somehow.
Yes. Yeah, but that
Non-separability and notions like that.
sure.
So it's, of course, it's
Yeah, but your question is what do we lose mathematically or what do we lose physically?
physics-wise.
Physics-wise, that's what I said. Is that when the electron moves, in principle, the nuclei should also react as they move. And here, that's not what we say. We say, okay, they just see the average. So the electron move, do whatever they want, and the electron later will move in the field of this electron, but not in this instantaneous motion. And it's the same. The electrons they move with fixed nuclei. So it's but if you are in the case where the nuclei move fast, for example, then the electron should respond in the same time scale. So this is this kind of thing that you lose. Okay. So it's some kind of correlation between the electron and the nuclei that you lose.
That we lose.
Yeah.
Some electron-nuclear correlation.
Yes. Yeah. You can. Yeah. In this term, you can write it like this. And to recover that, you can make a sum of several electronic states and nuclear states. Then you can start to get some correlation. But as I said, most of the time it's okay to do this, especially for the ground state. When you go to excited states, it can be difficult. But Krishna will talk about it when it breaks down. Mm.
Here there is no reason to think about stuff like entanglement. In the sense of writing it down like this, we simply throw away any such possibility.
Yeah, there is no correlation, no entanglement. No. Yeah. You neglect that. You lose that if you want. But that's also what I meant by correlation. For me, a correlation and entanglement are kind of the same thing. So you lose them. Yep. Yeah. Hmm. Okay. Any other questions so far? Sorry? Would be so you. Yeah. It's not the Laplacian. Yeah, you're right. Thanks. As I said, yeah. Hmm. Yep, you're right. And I didn't say it, but I use atomic units. So mass of the electron is 1 and so on, and h bar is 1. So, okay. All right. Okay, so how do we solve this? So I'll take. So we have to solve this equation here. Nope. How we solve this? There are several ways to do it. The most straightforward one, we have a differential equation. We can say, okay, we do a direct solution. Okay, we have several numerical methods to solve differential equation. We could go for it, but it's far too expensive, right? We can do it for system like helium, maybe H2, but that's it. For larger system, it's far too complicated, far too expensive to do it. Okay. Some people do it, but they really just focus on those small systems. Okay. I think the most used way to do it, the most standard method is the Hartree-Fock, and the related. So this is what I'm gonna talk about it. So it's the Hartree-Fock method, and oops, sorry, it's not easy to write with that. The post-Hartree-Fock. Okay, I use HF for Hartree-Fock. Okay, so for this, with this kind of method, you can treat system with, let's say, there are several post-Hartree-Fock methods. So I cannot tell you exactly which system you can treat, but roughly speaking, you can treat system with, say, 10 to 100 electrons. 100 starts to be really the limit, and you have to take a cheap post-Hartree-Fock method, but it's possible. And the third one, which I won't discuss at all, is density functional theory. It's a DFT method. Okay, this one is the cheapest ab initio, or some people would argue it's not ab initio, but I include it in this ab initio part. It's the cheapest ab initio method that we have, and here you can really go, I don't know, maybe between 100 and 1,000 electrons. Probably you can even, if you use some kind of cheap version of DFT, you can even go to larger system. Okay. This is really rough numbers. It's don't take it too seriously. It's just to give you a feeling. In terms of resonance width, I mean, to compute resonance width, I don't think we can use DFT. At least, as far as I know, no one derived any codes or formalism for using DFT and computing decay time, lifetime. Okay, so we can use hard-refog and post-hard-refog for that, and this is what I'm gonna focus on today. So the position of the resonance, you can get it with the DFT. This at least an approximation, an estimate of the position. I mean, in principle, if you want the exact position of the resonance, you also need to compute the width. They go together. Okay, but if you neglect this part, if the width is not too large, then you can get an estimate using DFT or yeah. And this, for example, OGA and so on, this has been done several times. That's true. For the position, DFT works. Works. That's fine. Yeah, it's yeah. Well, you can do TD-DFT to, or you can do delta DFT. So there are, I mean, it's not straight out of, it's not the normal DFT to get this estimate. You have to use some tricks, but within DFT you can get some approximation, some estimate. Yeah. But that's true. What Lance said is that you cannot take the DFT that is implemented in any quantum chemistry package, run and get this position. If you want that, I mean, in principle, DFT is a ground state method. So you get only the energy of the ground state. But there are some tricks to get excited state of DFT and also states where you have a hole in the core region. I mean the core orbitals. Okay. All right. So let's go to hard-refog then. So the idea of hard-refog is to write the solution of the Schrödinger equation as a single determinant. So we take our wave function and we say, okay, our wave function is just a Slater determinant built on one electron spin orbital. So I have n electrons, so I use small n just because the capital N was for the nuclei. So this n here is really the number of electrons that we have in our system. Okay? And the Ki, those are one electron spin orbital. Okay, so that's our ansatz for the electronic wave function. And now how we choose these spin orbitals? Well, we're going to optimize them such that the energy of the system is as low as possible. Okay? So we choose them to minimize the electron energy. Okay? We have some constraint because we want to keep the spin orbital orthogonal to each other. Okay? So we use Lagrange method to minimize the energy, keeping the spin orbitals orthogonal. Okay? Maybe I should write it here. So it's a orthonormal basis set. Basis. Okay. And if you solve, so this is much easier to solve now with this ansatz. So there are tricks. We use what we call self-consistent field because when you start to do the mathematics, you see that the operator, the matrix that you have to diagonalize depends on the spin orbitals that you don't know. So you make a guess of your spin orbitals, you build the matrix, you diagonalize it, you get a new guess, and you do that iteratively. Okay, I'm not going to discuss this part. Hartree-Fock is implemented in almost all quantum chemistry package, and there are numerical tricks and so on. But what you should just have in mind now is that that's much easier to solve. Okay, and once it's solved, you get two things. You get the spin orbitals. So that's the orbital we are used to talk about. For example, helium, atoms, we talk about 1s, 2s, 2p orbitals. This comes from Hartree-Fock theory, basically. Okay, and you get the energy of these orbitals. You get you get three things: the total energy, the orbitals, and the orbital energy. Okay. So this is what you get. So the chi, and I'll write it like this, or maybe I'll use epsilon. Okay. Those Hartree-Fock energy is going to be important later, so I'm going to draw them. So if I draw the energies, you have, once you solve this, you get orbitals where you have electrons sitting in it, so that this n electron here. Okay, so in my case here I have 8 electrons, right? 2 per orbitals, and the electrons where the orbitals where we have electrons sitting in, we call them occupied orbitals. Okay, sounds obvious why we call them occupied, right? They are occupied by electrons. And the other one, well, we don't call them unoccupied, we call them virtual. Okay. And those, they are really important for us because they can be seen as pseudo-continuum orbitals. Okay. So if you put one electron in this, it's like putting an electron in the continuum of your system. Okay. So those are really important for us. So it's pseudo-continuum orbital. Okay. So that's the Hartree-Fock theory in a nutshell. Okay.